Hello everyone, I am Angat Bhatia, PhD student at Concordia University. The topic of my today's presentation is optimized production scheduling for modular construction and manufacturing. In this presentation, I will briefly introduce the general problems in the modular construction production line and will also explain the research method developed to overcome the existing research gaps along with a case study where this method was implemented. Modular construction is a process where module components, for example, wall, roof, and floor panels, are prefabricated in a controlled factory environment and later transported on site to be installed as a building blocks. Modular construction is increasingly growing in popularity over conventional construction, given its potential to achieve shortened construction schedules and less material waste. However, these modules are customized, and thus there is a significant difference in design specifications of these module components, which causes variability in the process times of workstations and leads to an unbalanced production line. Moreover, in order to achieve the target completion time, production line managers make frequent changes in the production planning and scheduling. However, despite all the above challenges, this process of modular construction manufacturing supports a concept of standardized operating procedures, which allows to efficiently implement various technologies such as simulation, optimization, and so on, thereby enhancing the productivity of manufacturing these module components, which can greatly support in covering the additional demand for affordable houses required in the society and implement the philosophy of continuous improvement. In this respect, various researchers have developed certain methods to enhance the productivity of modular construction manufacturing process. For example, researchers developed the prediction models to forecast the process times of work at workstations along the production line in modular construction. Additionally, in the field of planning and scheduling, researchers developed multiple scenarios of production line schedules using discrete event simulation to determine the best scenario for balancing the production line. Moreover, in the field of optimization for production scheduling, researchers integrated GA and discrete event simulation in order to minimize the total makespan for modular construction production lines. However, there are following issues in these developed methods. First, manual and grid search CV were used to find the optimal parameters for machine learning algorithms. This approach is time consuming and does not ensure optimal parameters. Second, a limited number of scenarios were tested, therefore not giving optimal sequences of modules to be prefabricated in the production line. Therefore, to overcome these existing problems regarding the modular construction manufacturing scheduling, this research has a main objective of minimizing the total duration of prefabricating in the production line based on the sequences of module components at workstations. There are various sub-objectives to accomplish the main objective, such as to clean the RFID data by performing certain pre-processing tasks, identification of optimal module configuration for DNN model that is developed to predict the process times, development and development of a scheduling model that is optimal sequence of module components using GA. To achieve these research objectives, we have developed a method that combines deep neural network and genetic algorithm in order to solve the modular construction manufacturing scheduling problem. In this respect, the first step is to use the historical time data along with design specifications of module components as an input in the DNN model. Later, data pre-processing was performed to clean the data, followed by the development of DNN model and hyperparameter tuning using GA, which resulted in the predictive process times of module components at each workstation. These process times of module components were used as an input in the scheduling optimization model, whose objective is to find an optimal sequence of module components in order to minimize the makespan. In the first step, the process times are extracted from the timestamps collected by the case study company using RFID system. Later, pre-processing tasks, which includes removal of outliers and normalization of dataset using minimum maximum technique was performed. The dataset having been pre-processed, was divided into 80% training and 20% testing subsets. Based on the subsets, a DNN model is developed and GA optimization technique for hyperparameter tuning is used to identify an optimal model configuration and minimize the model's prediction error. The predictive process times of module components and the number of module components were used as an input in the optimization model. The objective of the optimization problem is to find an optimal sequences of module components to be prefabricated in the production line in order to minimize the make span. This optimization problem is subject to a set of constraints. Constraint 1 defines the production flow of module components, and constraint 2 represents the workstation capacity, which enforces each workstation can process maximum of one module at a time. The developed method was implemented on a semi-automated wood-based wall panel production line consisting of 7 workstations. The process starts at a framing station, followed by a sheeting and multifunctional bridge stations. It should be noted that interior wall panels are transported to the window bypass line to store them at the wall mixing line, that is a storage area, whereas exterior wall panels are transferred to the window door installation lines, where window doors are installed on the wall panels and transferred to the storage area. The wall panels are stored at the storage area as they await delivery to the sites. The process time at workstations were collected by the Modular fabricator company using an RFID system. In this respect, initial data visualization was performed to gain insights into the production line. For example, at sheeting station, the processing time of wall panel 3 was 9 minutes. Wall panel 4 was 12 minutes and wall panel 6 was 2 minutes. So this variation in process times affects the daily productivity of the workstation, causing an imbalanced production line. The next critical step in the case study was to develop a DNN predictive model by considering the wall panel design factors. In this research, the rectifier activation function is selected and the range searched for upper lower bound is 3 to 10 for hidden layers and 6 to 100 for number of nodes. As observed in the table, various workstations, for example framing, sheeting, nailing, and transfer table has an MAE of less than 2.5 minutes respectively. Later, the predictive process times were used as an input in the optimization model. A genetic algorithm was implemented with an objective of minimizing the make span. The number of wall panels considered for this optimization model are 46. The algorithm starts with an initial solution of make span equal to 4,359 minutes, and the algorithm converges to the best solution in 85 iterations with a make span equal to 4,352 minutes. To conclude, in the modular construction manufacturing, due to various design specifications, the production line requires dynamic changes to their production schedule. Therefore, we developed a method that utilizes DNN and GA techniques to solve the modular construction manufacturing scheduling problem. This developed method can assist production managers to efficiently forecast process times and develop production line schedules. In this respect, the future work in this research direction would be to consider module components based on multiple projects in the optimization model. Thank you.